Hello, in this podcast we're going to learn about force diagrams and component forces. Specifically, we're going to learn how to draw a force diagram to show the forces acting on an object. We're going to learn about component forces and how we include them in a force diagram. And finally, we're going to look at how having an object on an inclined surface changes the way we draw the force diagram and the component forces. Let's get started. Force diagrams are a way to represent the forces acting on an object. In this case, we're going to draw a force diagram on the log, and it's best to start with an XY axis. That's what these dotted lines represent. So the first step is to identify the object and shrink it to a point. So we're doing the log, and we're going to shrink it to a point, and we're going to stick that dot at the origin. Next, we want to draw all the forces acting on the object. And to do this, we're going to use arrows to represent the forces. The arrows are going to point in the direction the force is acting, and longer arrows mean stronger forces, and of course shorter arrows mean weaker forces. So we know there's a force pulling down towards the center of Earth. We also know that the ground is pushing up on the log. We can see from this picture that there's a force, the rope, pulling the log to the right, and we know that the ground is causing friction, hindering that motion, so it is pushing to the left. Next, we want to label all forces using our force label template. So capital F for force, the type of force, it's a gravity force, and it's Earth's gravity pulling the log towards the center of the Earth. Now, let's look at this force. It's a normal force because it's two solid surfaces, the ground and the log, and the ground is pushing on the log. Next, this force acting to the right is a tension force because the rope is pulling the log, and tension is a pull force. Finally, we have the friction force because the ground is pushing parallel to the log, and it's hindering the motion, so that makes it a friction force. Notice the ground is exerting two types of force. It's exerting a push force perpendicular to the ground, that's called the normal force, and it's exerting a push force parallel to the ground, and that's called a friction force. We do not want to draw forces that the object exerts on its surroundings. For instance, we know that the log is pushing down on the ground, but we don't want to show that force. We're only interested in the forces acting on the log. Similarly, we know that the log is pulling on the rope, but we're doing the force diagram on the log, so we're not showing that force that the log exerts on the rope. And finally, we want to use equality marks to identify pairs of balanced forces. Now let's look at these. First, horizontally, we know that these two forces are balanced because the log and the tractor are moving at a constant velocity, so we need to have balanced forces. If we look in the vertical direction, we know that vertically the log's not moving. It's moving horizontally, but it's not moving up and down. So we know that the gravity force and the normal force are balanced, so we need to use equality marks. So these slash marks or tick marks are called equality marks. Notice I used a double set for the vertical forces because while they're equal to each other, we don't know that they're equal to the horizontal forces. In fact, I'm pretty sure they aren't. So if we had just used single slash marks all around, we would be saying all four forces were equal to each other, and that's not the case. These two are equal to each other, so we use single slash marks, and these two are equal to each other, so we have to use a different unique set of equality marks, so we use double slashes. If we had a third pair of forces that were equal to each other, we would use triple slashes. Finally, let's move on and talk about component forces. So many forces don't act straight up and down or perfectly sideways. In this sketch over here, that's the case with this rope. Notice that the person is pulling the rope up and to the right, so it's not perfectly horizontal and it's not perfectly vertical. When that happens, the force is acting both up and right, and we can break the force into its component forces. Component just means parts. So we're going to break this force that's going up and to the right, we can break it into its horizontal component, That's the component that's acting sideways, and we can break it into a component that's acting straight up and down. And so when we do this, this single force that's acting up and to the right creates the same type of motion as if we had one force acting straight up and another force acting horizontally to the right. Let's draw the force diagram for this sled. So the first step is just like we did in the previous slide. We're going to draw and label all the forces acting on the object. So we have the down force acting on the sled, and that's the force of gravity. I'm using abbreviations now just to keep these labels smaller. Force of gravity, the earth acting on the sled. We have a vertical force, and we know that's the normal force of the ground pushing up on the sled. We have the rope pulling the sled, and notice the rope is going up and to the right, and that's a tension force because it's a pull force, the rope acting on the sled. And we also know that we have a force acting horizontally to the left, and that's the friction force, that is the ground acting or pushing to the left on the sled. Next, we want to identify forces that aren't on the X or Y axis. Well, you can see that these three forces are on the X and Y axis. They're perfectly vertical or horizontal, but the tension force doesn't lie on either axis. So in that case, we need to draw and label their horizontal and vertical components. So to do this, well, I'm going to start with the horizontal component, and I'm going to draw the arrow on the x-axis, and I'm going to draw it as far to the right as this force goes to the right. Notice if I draw a line straight down from the tip of the tension force, it comes this far on the x-axis. So that indicates how far my arrow should go for the horizontal component. This indicates how strong the horizontal component of this tension force is. And for my label, I'm just going to call it F sub Tx. I don't have to put the rope and the sled in anymore because I know that this is the X component of this tension force, and it involves the same two objects, the rope and the sled. Next, I have to draw the vertical component, and I'm going to draw the arrow up on the y-axis, and notice that I am drawing it as far up as the tension force goes. So the tension force goes this far up on the y-axis, so that's how far I'm going to draw this vertical component, and I'm going to label it F sub Ty. Finally, I'm going to use equality marks to identify pairs of balanced forces. Now, this sled is moving at constant velocity, so I know these horizontal forces need to be balanced, so I'm going to go ahead and put in my equality marks to show that the X component of the tension force is balanced with the friction force. That means that these two forces are equal in strength, they're just pointing in opposite directions. Now the sled is not moving up or down, so vertically it's motionless. That means that the vertical forces pointing up have to be balanced by the vertical forces pointing down. However, I'm not going to use equality marks because I have two forces acting up on the sled, the normal force and the Y component of the tension force. So those two added together equal the strength of the gravity force pulling down on the sled. But because these two added to each other equal this, neither of these forces are equal to this one, so I'm not going to use equality marks. So you can have balanced forces where two forces acting in one direction balance out a single force acting in the other direction. It's just in that case, it's not a pair of forces that are balanced, it's a triplet of forces, and you only use equality marks to identify pairs of balanced forces. Finally, let's take a look at how we handle objects that are on inclined surfaces and the role component forces play. Objects on inclined surfaces are going to move parallel to the surface. Therefore, we need to rotate the X and Y axes so that the X axis is parallel to the inclined surface and the Y axis is perpendicular to it. In terms of forces, gravity acts straight down. It does not act on the y-axis. And of course, its x component is going to be parallel to the surface on the x-axis, and its y component is going to be perpendicular to the surface on the y-axis. The normal force is perpendicular to the surface and it balances the y component of the gravity force. Other forces such as friction, traction, tension, etc. are parallel to the surface and they are going to either aid or hinder the motion. In this instance I showed these forces acting uphill, but they can also act downhill. The x component of gravity, however, will always act downhill. And finally, the x and y components are also known as the parallel and perpendicular components. Well, this wraps up our lesson on force diagrams and component forces. I hope this helped, and have a good day.